All right, well, welcome to Friday. So this is a huge Friday. I don't know if you realize how big this Friday is, but we are at the midway point of the quarter. Yep, from here on out, it's downhill. So you've made it halfway. We're almost there. Anyway, so today what we're going to do is we're going to start looking at applications of the derivative, things that we use it for. And that's what chapter 4 is going to be all about. And today's topic, we're going to talk about these things called related rates, which are exactly what they sound like. They are rates of change that are related to each other. Ooh. Anyway, so that's our plan for today. But of course, as always, before we do that, are there any questions on homework or anything we've talked about in class that we'd like to discuss?
I have a couple. So I was wondering if you could go over 3.7, question 5, and then maybe question 16 also.
Okay, 3.7, numbers 5 and 16. We can definitely take a peek at those. Anything else? All right, well, let's go run over there and take a look. So I'll share my screen here. All right, so good old derivatives of inverse functions. All right, so here's number 5. So we've got a function x squared minus 3x minus 3, where x is greater than 1.5. Before we go any further, just real quick, notice that this guy, x squared minus 3x minus 3, that's quadratic. This graph is a parabola, a happy parabola. And we know that that's not 1-to-1. But by them saying, okay, x's are greater than 1.5, we basically erase half of the parabola. And now it is 1-to-1. So just FYI. All right, so we've got ourselves a function. And then it says we want to find the derivative of the inverse with respect to y at y equals 4. Okay, so basically, we need to find the derivative of the inverse. So we're going to use the original function. Now, we could solve that original function for x and then, find that inverse and differentiate and do it explicitly. But I don't want to do that. That's a little too much work. All right. So what we're going to do is make use of the fact that we know inverses have derivatives that are reciprocals. So let me go ahead and share a whiteboard, and I'll kind of walk you through this one. Okay, so we have f of x equals x squared minus 3x minus 3. So what we're trying to find is, I know that they wrote it as ddy. I'm going to go ahead and write it like this, but except we were told a number. We were told we want to find the inverse of 4. Okay, so what we know, since it's an inverse, is that this is 1 over the derivative of the original function evaluated at f inverse of 4. So where this comes from is what we proved. Oh goodness, that was probably last week at some point. But the relationship we saw between inverse functions is that their slopes are reciprocals. So what we need to do is take a derivative of f. Well, that's easy enough. This is just power rule. So we're going to get 2x minus 3. And so now the question is, what do we plug in? Well, we don't plug in 4. 4 is what goes into the inverse, which means it's what comes out of the original function. So in essence, we need to know what do we plug into the original function to get 4. So I need to basically answer this question. What number, when I plug it in, gives me 4? And then that's the number I'm going to plug into F inverse. All right, so before I go any further, we okay with this ish?
Yeah, that makes sense.
Okay, so now subtract my 7. I've got a quadratic. I need to solve this one. Doesn't look like it factors, but that doesn't scare us off, right? So we get good old negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have 3 plus or minus 37 all over 2. All right, so the question is, which one do we plug in, the plus or the minus? Because we can only plug one number in. Well, that's where that restriction comes into play. Remember, it told us that we were looking at x's that were bigger than 3/2. Might have said 1.5, but regardless. So the only x's that work are the ones bigger than 3/2. So that tells me that the x we're going to use is the one with the plus. So this x gives us 4, which means when we plug 4 into the inverse, it's going to give us 3 plus root 37 over 2. So that guy then, we're going to fire into the derivative. So I'll do that down here. So f prime of 3 plus root 37 over 2 is going to equal 2 times 3 plus root 37 over 2 minus 3. This is going to simplify a lot. The 2's cancel from that multiplication, and then the 3's cancel from our subtraction. And so what we're left with is just the square root of 37. So the derivative of our regular function, the original function, is root 37, which means the derivative that we're looking for is going to be 1 over root 37. They're reciprocals of each other. So notice that we didn't do anything with the inverse. We didn't find its equation, didn't actually do its derivative or anything because we didn't need to. Knowing the original function was plenty for finding this. So that's basically the process with any of these. Whatever you're plugging into the inverse comes out of the original function. So you have to solve for the original x. And then you put that x into the derivative of the original function. Right, that's square root of 37. And then take its reciprocal. All right, so is that better for number 5?
Yeah, the only thing is you lost me on the algebra where you got 3 plus or minus 9 or root 9 plus 28 over 2.
That's the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So just write in your notes so you can go back and look at it. It's the quadratic formula. We don't have time to go into that. Tim. So, but you can find that in any algebra book.
I have a quick question.
Sure.
I was just wondering, when we're solving this type of problem, but with, but it's like a trig version. I just got a little bit confused about plugging in the inverse derivatives that we already have. Does that take away the step where you have to flip it at the end, or not?
Okay, so when you said we plug it into the inverse derivatives, what do you mean exactly by that?
Like, wait, hold on 1 second. I'm trying to find it in my notes here. Like, I guess when we did the proofs where we found the inverse derivative, like tan inverse and stuff, I was just confused about like how we're using that in this context. Like, because we've already solved that, does that take away the step at the end where we have to flip it, or is that?
Oh no, that still did happen. Let me clear this real quick.
Okay.
And let me show you what I mean. So like, let's say we're looking at inverse tangent. Okay, so f of x is tangent of x. And so we're trying to find the derivative of inverse tangent, right? So think about that means we're going to do 1 over f prime evaluated at inverse tangent. So tangent, its derivative is secant squared. So that means it's still going to be 1 over secant squared of inverse tangent. So I'm still doing the reciprocal. I still have 1 over. It's just now that we're composing these trig functions, we can actually simplify that a bit. And this is for sure where the difficulty in the proof comes in, because this guy, inverse tangent, is going to be an angle. That's what the inverse trig functions do. You plug in the value and it gives you the angle whose tangent was that. So basically, this is the angle such that tangent of theta is equal to x. All right, that's what inverse tangent of x does. And what we're doing down here is we're doing secant of inverse tangent, which in essence is secant of theta, right? Because I'm just renaming that guy theta. So basically what we want to know is, given that tangent is equal to x, what is the secant equal? And that's what we did to get that formula for tangent, is we basically drew a little right triangle, call that guy theta, and we know that the tangent is equal to x, or also you can think of it as x over 1. So here's a triangle with an angle whose tangent is x. And now we want to find the secant of that angle. Well, secant is 1 over cosine. Cosine is adjacent over hypotenuse. So we actually need to find the hypotenuse. Well, you can get that from the Pythagorean theorem. Let me actually write that out for you down here. So you remember your good old Pythagorean theorem, a squared plus b squared equals c squared. We're trying to find c. A is 1, b is x. So if you want to get c, you just take a square root. We got the square root of 1 plus x squared. So that's where that came from. And so then again, secant, if we just use the relationships between sides to give a secant, this is hypotenuse over adjacent. So that's the secant of theta. So if we come back here, remember what we're doing is we're squaring the secant of theta. So we're going to 1 plus x squared and square root squared. The square root and the square cancel each other, and that's what gives us that formula. So Alia, when you asked about, in here, does this make it so we don't have to do the reciprocal? No, we absolutely still did. It's just we were able to simplify it, and that simplifying had zero to do with calculus. Like all of this stuff, all this colored stuff, none of that is calculus. That's all trig. That's all pre-calc. The calculus steps, I mean, there were two of them. The calculus steps were right here when we differentiated tangent, and right here when we did the derivative of the inverse tangent is the reciprocal of the original derivative. That's it in terms of the calculus. The rest of it was trig to simplify.
So if you were trying to find an inverse function, sorry, there's like a saw in the background.
It's all good.
If you were trying to find a derivative of an inverse with something instead of x, and you're like using the chain rule, I guess my question is like, do you not flip the 1 over 1 plus x squared part of it because
Okay.
it's been flipped?
I see what you're saying. So if you have something like f of x equals inverse tangent of, let's say, x squared plus e to the x. Yeah, something like that, you mean?
Yeah.
Where we're going to do now chain rule in here. Okay, so the fact that we have this rule means that is the derivative of inverse tangent forever. We've already built it. So we don't actually have to use the flip anymore because we already did to create that rule. So what that's going to do here is basically this. We go to the derivative and you go, all right, when you do inverse tangent, its derivative is 1 over 1 plus the stuff inside squared. Right? Just think about all this stuff, call it u, for example. So we have inverse tangent of u, we get 1 over 1 plus u squared. But then the chain rule would say multiply by the derivative of what's in here, which would give us 2x plus e to the x. So at this point, no, I'm not flipping over anymore because I flipped over one time to create this rule, and now I've got this rule. That is the derivative always.
Okay, so you just use the chain rule if you're going to plug that in.
Yep.
Great, thank you.
Yeah, you're welcome. Yeah, once you develop the rules or whatever, then that's it. You don't have to go through the steps of building it again. And that finding the reciprocal was used to build this rule. All right, so is that good for that one? Okay, so then the other question, the other one that Tim asked about was 16. All right, so 16. Pole stands 75 feet tall. An angle theta is formed when wires of various lengths of x feet are attached from the ground to the top of the pole as shown in the figure. Find the rate of change of the angle d theta dx when a wire of 151 feet is attached. All right, so basically we need to start by figuring out an equation for theta that involves x. right? Because if we're going to find this derivative, we kind of need to know how they're related. But we can use trig for this. So think about that angle theta and that guy x. We also have another side, this guy 75. So which trig function relates these two sides, the 75 and the x? Which trig function is that going to be? All right, so Eric just threw in the chat sine, which I think is perfect. Remember, sine is opposite over hypotenuse. So what we're going to have is that the sine of theta is going to equal 75 over x. So let's go to a whiteboard here. So I'll redraw that picture real quick. So theta x 75. So we have the sine of theta is equal to 75 over x. So if we want to solve this for theta, then theta is going to equal sine inverse of 75 over x. And now we can find d theta dx. All right, so before we actually differentiate, how do we feel about this right here, getting this equation? Do you see where it comes from? All right, so I guess we're good. All right, so now we're going to use the fact that we know the derivative of inverse sine. So if y is equal to inverse sine of x, then y prime is 1 over the square root of 1 minus x squared. I'm pretty sure that we built that once upon a time. If we didn't do that one exactly, we did one similar to that. It's kind of like what I just showed you, reminded you with the tangent inverse just a second ago. So if we jump and use that here, this is going to require chain rule, but we can handle that. So this is going to be 1 minus 75 over x squared inside that square root. Because basically I just said let's let u equal 75 over x, right? So sine inverse of u is 1 over the square root of 1 minus u squared. But then we need to multiply by the derivative of u. Well, think of that as 75x to the minus 1. And we get minus 75x to the minus 2. So there's the derivative. So this is telling us how the angle is changing as that length x changes. If we start letting x get longer, then theta is going to change according to this formula. If we let x get smaller, same thing. And so now to finish this question off, I don't remember what it said, which length it said, but it was like, figure this out when x is equal to like 150 or something like that. We would actually just plug that number in and see what we get. Oh, 151. Thanks, Leah. Again, I don't really care what that number is, so I'll leave that for you. But basically, you would just plug that in now and you'd find out how that angle is changing. All right, so there you go. That's how we can find this. But I want to show you something else, and I want to show you how we could have done this a little bit easier. So let's come back here where we have sine of theta equals 75 over x. Instead of solving for theta, let's do implicit differentiation. So the derivative of sine is going to be cosine of theta times d theta dx. Think of theta like your y. So you have cosine theta times theta prime. The other side, we're going to get minus 75 x to the minus 2. So d theta dx is going to equal minus 75 x to the minus 2 over the cosine of theta. Now, these don't look exactly the same because we still have theta in there, but we can get cosine of theta if we come back and we look at the original picture. Cosine of theta, that's equal to adjacent over the hypotenuse. Okay, well, we could use the Pythagorean theorem to find this adjacent side. And it's going to equal x squared minus 75 squared. If you do the good old a squared plus b squared equals c squared. So the cosine of theta is going to be that guy divided by x. And it turns out that these two pieces are identical. If you were to take that x and put it through into the square root, basically make this a square root of x squared and then simplify, you get exactly the same thing. So we could have done this with implicit differentiation. And what's nice about that is you don't have to remember the derivative of inverse sine. Take that for what it is. It's an alternative approach. But this kind of brings me back to something I think I mentioned with you guys, although it could have been my other class, about how math is like, you can make it yours. There's more than one way. This is a really good example that depending upon how you want to approach this, there are different ways of getting there, and some work really well for some folks and others work better for other folks. And, you know, just the more you know, the more options you have, and the more you can craft it and make it your own. Anyway, so how's that for number, whatever that was, 16? We good? Man, you guys are really quiet today. I shouldn't have told you we were at the halfway point. I think I demoralized you. Like, oh my God, we're only halfway. I'm definitely that, oh yes, we're halfway, we're almost there. Even those words, right? Halfway, almost there. But from here on out, the days are getting shorter. Oh, you want to take a photo of that screenshot? Yeah, hold on a second, Henry. Let me put that back up. So I'll put that up here for another second or two. All right, cool. Okay, so today we're going to talk about related rates. And like I said, related rates are exactly what they sound like. It's when two things are related to each other and we want to find out how their rates of change are related. All right, so let me just give you some examples of where this could happen. Let's go with a simple like ecology kind of example. So living in Tahoe, and I know not all of you are in Tahoe, but for those of you who are around, you know what I'm going to talk about here, or you're going to understand this. But we have quite a few coyotes that live in the Tahoe area. And in fact, every one of you is a coyote. That's our mascot for the school, right? Anyway, so we got a bunch of coyotes, and we also have a bunch of squirrels. And coyotes like to eat squirrels. So if you were to look at, say, the change in population of coyote, it's going to depend on the change in population of squirrels. If there are more squirrels, then the coyotes are going to have more food, and they'll probably be able to, the population is going to be able to grow. Versus if the squirrel population dies off, then the coyotes are going to have more trouble, and so on, right? So there's an example of rates of change in coyote population, change in squirrel population, that are going to be dependent upon each other, right? Because like the squirrels, their population will change too. If there are fewer coyotes, there are fewer predators, so the squirrels are going to be able to, their population is going to be able to grow. And alternatively, if there are lots of coyotes, then the squirrels are going to die out. So those would be rates of change that are related to each other. So those would be related rates. Okay, or imagine that you have a balloon that you're blowing up, a nice circular balloon. Here are two quantities who are related to each other, so their rates of change would be related to each other. One would be the surface area of the sphere. The other would be the amount of air we're blowing in. Right? So if I increase the rate at which I'm blowing in air, I'm going to increase the rate of change in the surface area. Right? The more air I blow in, the faster the surface area is going to change on this thing. Okay, so there are two quantities that are related to each other, and so their rates of change are related to each other. So, I mean, there are tons of these. Basically, if you have two quantities, one affects the other, then the rate of change in one will affect the rate of change in the other. And that's what we're talking about with related rates. Okay, so let me hop to the whiteboard and we'll play around with some of these, and you'll see what this has to do with what we've been talking about up to this point. So give me 1 second and I'll see you at the whiteboard. All right, so give me 1 second here, folks. I just realized that the glare had moved onto the whiteboard, so we'll limit that with just the light. Okay, so with related rates, basically here's how these are going to play out. What we're going to want to do anytime we have one of these is figure out a relationship between the quantities that are changing. And then we're going to use some calculus to figure out how their rates are related. Now, I'm going to warn you, these are all word problems. Go ahead, groan now, get it out of your system. All right. Applications, if you haven't figured this out yet, in math, applications tend to be word problems. And most of you are going to go into the sciences, engineering, and all that. It's all one big word problem. You're never given the equations. You got to, figure them out. So just realize these are word problems. But once we find the relationships between these quantities, we're just going to be able to use our calculus and go. So as an example, suppose that we've got this. All right, we're going to be just hanging out down here on a beautiful day, enjoying Tahoe and sitting out there, and we see a bird flying towards us. So we see an eagle that's flying towards us. Here comes an eagle flying towards us. And I just realized I'm in the middle of that glare spot. So let me move this down here. All right, so here we are watching this eagle that's flying towards us. All right, now to see that eagle, we have to tilt our head in such a way at an angle so that we can actually see it. So maybe we're actually, looking through binoculars, and so we're having to pivot ourselves so that we can actually see that. All right, now think about this. When that eagle gets closer to us, is the angle that we have to view it at changing? And if so, is it getting bigger or is it getting smaller? All right, so a couple of you guys are saying bigger, it's increasing. Yeah, as that bird flies towards us, that angle has to increase. I mean, just here, I'll try to tilt my head as I'm watching an imaginary bird fly towards me. It's coming towards me. Oh, it's almost above me, right? And so you see me tilt my head to a greater angle. All right, so here are quantities that are related to each other. We've got that theta, and we've also got the distance that that bird is away from us. As x changes, theta changes. So those quantities are related to each other. Their rates of change are going to be related to each other as well. Okay, so let me give you some more information. Let's say we know that that bird is flying 30 feet above us. Okay, so it's 30 feet above us. It turns out that this is enough information for us to see how the change in the angle is affected by change in the position. Okay, so let me show you how we could build this. So first of all, let's get an equation that involves theta and x. I'm going to use trig because I've got a nice little right triangle here. And what I know is that the tangent of theta is equal to 30 over x. So if you were to tell me how far away that bird was, right? You tell me, okay, the bird is 100 feet away from you horizontally. I plug in 100, do my inverse tangent, I can tell you what the angle is. Or you tell me it's only 5 feet away horizontally. All right, I plug that in, inverse tangent, I get my theta. So you tell me how far it is, I know exactly what the angle is. But this is the relationship. Now, what I'm actually interested in, though, is I want to find d theta dt. I want to see how is that angle changing with time. All right, so as that bird's flying, how quickly do I have to pivot my head? That's d theta dt. All right, well, because I've got this relationship, I can now differentiate. So I'm going to take a derivative, both sides of this, with respect to t. Hey, we're implicit differentiating. What? Yeah, so this is implicit differentiation. But notice I'm not differentiating with respect to x. I'm differentiating with respect to t. I want to know how these things are changing with time. Okay, well, that doesn't really matter. That doesn't change what we do. we know that when we do implicit differentiation, anything that's not the variable that we're differentiating with respect to is treated like a constant, but then, or treated like normal, but then we have to attach the y prime, or in this case, the theta prime, and so on. So here, check out how this works out. So tangent of theta, its derivative is secant squared theta, but then by the chain rule, we need to multiply by a d theta dt. Just as if that had been tangent of y. Right? I mean, it's the same idea. Go to the other side, 30 over x. Well, if I differentiate that, I'm going to get negative 30 over x squared. That was just power rule. But again, I need to multiply by dx dt. Because that's the chain rule. X is a function of t. X is a function of time. It's implied that it's a function of time. So I have to do the chain rule. All right, so if I actually solve this for d theta dt, I'm going to get minus 30 over x squared times cosine squared theta times dx dt. It's a cosine now because I'm dividing by secant. 1 over secant is the same as cosine. I would just rather have cosine. If you want to leave it as minus 30 over x squared secant squared, go for it. Doesn't matter. All right, well, check it out. Here are two rates of change. The theta t and dx dt, and they are related to each other. Hence the name related rates. All right, so in essence, if I wanted to know how quickly that angle is changing, how quickly I'm having to pivot my head upward to watch this, it depends on a couple things. It depends on x, which was how far away the bird is. And that should kind of make sense. If the bird is really far away, even as it's flying towards you, that angle doesn't change very quickly, right? If the bird is very close to you, that angle changes very quickly. So it does depend on x. It also depends on the angle. Well, I mean, that's still how far away the bird is, right? If the bird is far away, you've got a small angle, bigger angle, so it comes closer. So all of this stuff is dependent upon where the bird is. But it also depends on dx dt. So that's the change in the distance away with time. I'm curious if you recognize what that is. So that goes by a different name. Like it goes by something that you could tell anybody out there. If they went, what the hell is dx dt? It's really easy to describe it. Anybody recognize what that is?
Is it the derivative with respect to time?
Okay, it is a derivative with respect to time, but that's not what I'm going for. I'm going for like a word everybody knows, non-calculus word.
Velocity?
Yeah, it's the speed. It's the speed of that bird. If we know how fast the bird is flying, that's its change in distance with time. So a lot of these rates of change are actually quantities that we know. And in this case, this is actually the speed of the bird. I'll go with velocity. I think that was that Ollie who said that? If not, I'm going to give you credit for it. So yeah, but yeah, so that's the velocity of the bird. How fast that bird is flying is how x is changing. And I put velocity because it can be positive or negative. It can be flying towards us or away from us, right? away from us would actually make that a positive because x is increasing. Flying towards us would make that negative because it's decreasing.
Wait,
But
sorry, where
it
did
should
you-
make sense. I'm sorry, go ahead.
Sorry, where did you get that cosine squared?
I divided by secant. And 1 over secant is cosine.
Oh, gotcha. Okay.
But this should make sense too, that how quickly we have to change the angle depends on how fast the bird is flying. Right? If the bird is just lollygagging, barely moving, we're not going to have to go very quickly. But if it's just like taken off, then that theta has to change relatively quickly. Right? So when we do this, once we get our equations and we differentiate, you're going to see why, like if you think about it, it's going to totally make sense why all this stuff is in there, why it matters where the bird is, why it matters how fast the bird is flying. But now we've got this, and so we could actually use it to calculate things. Right? If we want to actually know some specific rates of change at various locations, it's just a matter of plugging in the numbers. So this is the kind of thing we're going to do. Sometimes, I mean, yeah, we'll use right triangles sometimes. Sometimes we won't. It just sort of depends on what the situation is. But this is an example of a related rates question or a problem.
So if you're starting with d dt and then you have different variables on each side, then you just put that variable onto the top of the d dt, and then if there's any other variable, then you just multiply by the derivative of that. Is that right?
Yeah, we're just multiplying by the derivative because that's the chain rule. It's just like implicit differentiation. Right? You think about when we did implicit differentiation, we were differentiating with respect to x. So anytime we had something that wasn't x, y, right? We differentiated like normal, but then multiplied by y prime, which would be a dy dx. It's the exact same idea here. Now, anytime we run into something that's not t, we differentiate like normal, but multiply by a d whatever dt. So a d theta dt or a dx dt. Yep, it's chain rule. It's implicit differentiation, which is chain rule, just like before. Okay, so let's actually take a problem, a word problem, and let's kind of go through it and see how we could actually do this as a related rate question. So I'm going to share something from my other screen. So give me a second here. It's basically a series of related rate questions. And we'll walk through one of them. Okay, so here are a whole bunch of related rates questions. Right? I know it says group exercises, but we're going to just talk about them together. But here are a whole bunch of them, right? So like, look at the first one. It says, at a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 20 cubic feet per minute. The diameter of the base of the cone is approximately circular, or sorry, approximately 3 times the altitude. At what rate is the height of the pile changing when it is 10 feet high? All right, so first of all, I know you're reading this and this is blah, 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 right? But I want you to pick out some things to help you realize this is a related rate question. So first of all, look at what the question asks. At what rate is the height of the pile changing? It's asking you for a rate. Well, that's a rate of change. And this one specifically, the rate of change in the height. So if we called our height, say, y, this would be a dy dt, or if we call it the height h, it's a dh dt, or however you want to think about it. Okay, so it's asking us for a rate of change. Now, it's also giving us a rate of change. Look in the first sentence. It says that the sand is falling off a conveyor onto a pile at a rate of 20 cubic feet per minute. Okay, so they gave us a rate of change. You see the word rate. It's falling at a rate of. Okay, so that's a rate of change. But the question is, what is it a rate of change in? Like, what is it? Is it like, you think about what it was asking us was to find the change in height. Well, what is this rate? Well, a little tip for you when you have something like this and you're trying to figure it out is to look at the units. So you notice it says it's a rate of 20 cubic feet per minute. So the per minute tells me that this is a dt. So the question is, what is cubic feet? So do you guys know a quantity whose units are cubic feet? All right, well, I'm not seeing any guesses and nobody's chiming up. That's volume. Volume is cubic feet, cubic meters, cubic inches, cubic anything. If you have square feet, square inches, square meters, that's area. All right, so this one would be a volume per minute. So for number A, they give us a rate of change in volume, and they're asking us to find a rate of change in height. So those are the quantities that are related to each other, volume and height. So what we need to do is see if we can get an equation that relates volume and height so that we can differentiate. Okay, so I'm going to stop sharing the screen for a second so we can come back to the whiteboard and we'll see if we can create said equation. So I'm going to start by drawing a picture. I'm a huge fan of drawing pictures, as you guys know, and I think with the related rates, it definitely helps. Okay, so here's our conical pile of sand. Right, we got our conveyor belt that's coming up that's dropping sand onto this pile, right? But we've got a conical pile. So the first thing I'm going to do is think about volume of a cone. All right, now, I'm not expecting that you guys all know the formula for a volume of a cone. Okay, I don't. I do expect that you could find it, though, if you needed. And we know that the volume of a cone is given by 1/3 pi r squared h, where r is the radius of the circle, and then h is its height. Okay, so again, I don't expect that you know this. Some of you might, and if you do, awesome. If you don't, you should at least be able to Google it or something. Right? So we know that the volume of this thing is given by 1/3 pi r squared h. So that's cool. We now have a relationship between v and h. The only problem is it has r. And if we keep dumping sand onto this pile, the radius is going to get bigger. It's just going to get bigger. But we were told something about the radius when we were given those words. So let me go back to the, I'm going to share the screen again so you can see what it says here. So if we look at that, it says the diameter of the base of the cone is approximately 3 times its altitude. Okay, well, let's just go to this. So the diameter of the cone, that's actually 2r. And we know that that diameter is about 3 times the altitude. So we've got 2r is equal to 3 times h. Okay, so let's go back to the whiteboard. So we've got 2r, the diameter, is approximately equal to 3 times the altitude, 3 times h. So what we can do is actually solve this for r. So 3 halves h. And we can replace that in here. So let me do that. I'm going to run back up to the top of the board, and let's see if we can simplify this a bit. So the volume is 1/3 pi r squared. So pi times r, which is now 3 halves h squared, times h. If I square, simplify a little bit, we get v is equal to 3 pi h cubed over 4. So the h cubed, hopefully you see where that comes from, h squared times h. And the rest of this gets us here. So I just noticed that we are at the end of class. I want to finish this example. All right, so just please hold tight here for just a couple more minutes. All right, so now we've got this relationship between v and h. We're ready to differentiate. So we'll differentiate both sides with respect to t. So on the left, we're going to get dv dt, right, the derivative of v. On the right, the 3/4 pi is constant. H cubed, its derivative is 3h squared times dh dt. And so now we have a relationship between dh dt and dv dt. So for this specific problem, it asks us to figure out dh dt. So I'm going to solve this thing for dh dt. It's going to be 4 over 9 pi h squared times dv dt. Just divide all that stuff over. And so if we want to answer this question, if we want to figure out how the height is changing as we're dumping on sand, we need to know 2 things. One, we need to know how tall the pile is. The taller it is, the slower the height is going to change, because there's just more volume to fill up. So we need to know a height, and we also need to know how quickly stuff is coming on, which it totally makes sense, right? If there's more sand coming on quickly, then the height is going to change faster. If it's slowly being added on, the height will slowly change. So that's kind of what I was talking about before with the bird example, is that it makes sense that it should depend upon both of those quantities. Well, now's where we would plug in the numbers that they told us. So I'm not going to go back to that screen, but I'm going to tell you that we were told that the height was 10 feet. So we were looking at the rate of change when the height was 10 feet. And we were told that this was coming on at 20 cubic feet per minute. So we punch those numbers in, we get what we get. But that's the rate of change in the height of this cone. All right, so these are related rates questions or problems. We will talk more about these on Monday. Don't worry, we just barely scratched the surface. But we'll also start developing kind of a process, what we do every time. And we'll talk more about that when we do some more of these next week. Okay, so unfortunately, we're out of time for today. I'd love to spend a little more time talking about these right now, but yeah, I guess we're done for the day. All right, so just so you know, coming up next week, it's just going to be applications. We're going to continue talking about related rates, and then we're going to move on to other things that we do with derivatives. And that's pretty much what we're going to be doing for the rest of the quarter, is talking about what good differentiation is now that we've got all the tools. All right, so yes, Mariela, we do have an exam next Friday as scheduled. In terms of what it's going to cover, I can't tell you right now. I'm not really certain. But I do know like it will pick up from where the last exam left off, which again, I'm not really certain what that is. But I can tell you for sure that this exam next time is going to be a lot of differentiation, right? It's going to be a lot of derivative stuff because that's what we've been doing for a while. So definitely know product rule, chain rule, quotient rule, you know, the inverse derivatives, implicit differentiation, derivatives of logs, exponents, all that good stuff. But we'll talk more next week about what it specifically covers. I just don't know yet what it's going to be. All right, you're welcome. All right, any other questions before we head out? Okay, well, hey, have a great weekend and don't get discouraged by this. I know you just saw this and now you're probably like, oh crap, we are in for a world of hurt. It's not that bad. It's not that bad. It's just a matter of sifting through the words to get what we need. Anyway, all right, well, hey, you guys all have an awesome weekend and I will see everybody on Monday.